Okay, today we're going to talk about polynomial functions in section 5.1, 5.2. We won't get to all of it, but we'll talk about rational functions. Now, polynomial function, we've got a few definitions here we need to pay attention to. And the first one is polynomial function, the exponents are positive integers. The exponents are positive integers if it's going to be a polynomial function. One of the things that we talk about now was whether or not the curve is smooth and continuous. That thing that we reviewed in the other section was a good example of that. You say, well, how can a curve not be continuous? Well, one of the easiest ways for me to show you that a curve is not continuous is to draw the graph of something like this. If you draw this graph, when x is 1, y is 1, and when x is 2, y is a half, and when x is a half, y is 2. So it goes like this. Then also you put in minus 1, 1, and it goes like this. So that's two good curves, but it's not continuous. Continuous, the easiest way to think of it, if you can put your pencil and stay on the curve for all pieces of it, it's continuous. Or here we would have to jump in order for it not to be. But this is a perfect example of to talk about something else, and that's the idea of a limit. Now, limits intuitively are really easy to deal with. In other words, we can see what it means. So let's take it, this example right here. What is the limit of 1 over x as x approaches, let's say, infinity? Well, as x gets bigger and bigger and bigger, then 1 over x gets smaller and smaller and smaller. So the limit of this is approximately 0. Now, I want you to notice it doesn't say that it ever becomes 0. It says that it is approximately 0. The graph that I have up here is a really good example of that. As x gets bigger and bigger and bigger here, 1 over x gets smaller and smaller. So the graph keeps getting closer and closer and closer to the x-axis, but it never gets to the x-axis. It simply gets closer to it. Okay, and that's another definition. An asymptote. I want you to listen carefully to the definition. It is a line that my graph approaches for extreme values of the variable. Keep in mind the word extreme, for extreme values of the variable. So in our case up here, when x got very, very large, then 1 over x got very small, close to 0. So for this particular graph that right here, the horizontal asymptote of the graph that I just showed you is the x-axis. It is y is equal to 0. That's my line that it got close to, but it didn't touch. Now, it may cross the horizontal asymptote for small values of the variable. Keep in mind that the horizontal asymptote, your graph may cross it for a small value, but it never will cross it for large values. Now, another very, very important statement is a vertical asymptote. Never. It will never cross the vertical asymptote. And we're going to see, well, this is a perfect example of it right here. For this graph right here, my vertical asymptote is the y-axis. That's x is equal to 0. Well, look at my equation right here. X can never be 0. So as simple as this graph is, it gets a lot of these ideas in our mind. Number one, the idea of a limit. As something gets, one of them approaches something, something else approaches another value. It gave us our horizontal asymptote of y is equal to 0. It also gives us a vertical asymptote of x is equal to 0. Okay. But the idea of horizontal and vertical asymptotes, we're going to cover more in the next section than we are in this section. One of your homework problems deals with something like this. And he wants you to get the idea of what this pattern looks like. Well, first of all, let's go back to what we had earlier and talk about a shift. This is going to have a horizontal shift of 2. So I know that something happens at 2. And in this case, I plug in 2. 2 minus 2 gives me 0. So at 2, I get 2, 0. Now this thing is raised to the 4th power. So I want you to watch what happens when I let x be 2 and 1/4. Now, when I let x be 2 and 1/4, I get 2 and 1/4 minus 2, which is 1/4. But 1/4 raised to the 4th power is 1/64. So what that says is that this thing is very flat. It flattens and it rises real quick like. Now, it looks like you think it's a parabola, but it's not a parabola because it is much flatter across the bottom because of this 4th power that we have. Okay, shift gears a little bit. We're going to make a 3rd degree polynomial. 3rd degree polynomial. I'm going to give you the 3 answers. And the answers that I'm going to give you are 1, minus 1, and 2. So I'm giving you the answer. We simply want the equation. So one of the answers is x is 1, x is minus 1, and x is 2. So x minus 1 is a factor, x plus 1 is a factor, and x minus 2 is a factor. Now, we're going to FOIL these two together because they're the difference of 2 squares. The middle term is going to fall out. So I'm going to get x squared minus 1 and multiply by x minus 2. Now we can FOIL this again, and this gives me x cubed minus 2x squared minus 1x plus 2 is equal to 0. So we have created a 3rd degree equation that has the roots 1, minus 1, and 2. Now keep this in mind because it's definitely a test question, and it's very, very simple to do. You simply work backwards with it. Okay, we've got a couple of concepts that we want to study in this type of equation. First of all, we want to talk about the multiplicity of the factors. Well, in this factor right here, x plus 1, then x is equal to minus 1 is going to be the intercept, because when x is minus 1 and plus 1 gives me 0, so it's going to cross when x is 0, y is going to be 0. So it has what we call in this case, multiplicity of 2. Now, in this factor, x is equal to 6, and it has multiplicity of 1. Now, the big deal is this. When the multiplicity of the factor is even, it bounces at that point. Listen again, when the multiplicity of this factor is even, it bounces at that point. When the multiplicity of this factor is odd, it goes through that point. So let's look at it from a graph standpoint. We know that when x is minus 1, y is going to be 0. And we know that when x is 6, y is going to be 0. Now, since it's a polynomial function, that means it has to have a y-intercept. Well, to find the y-intercept on any graph, you let x be 0. So if I let x be 0, I got minus 6, then minus 2 is 12. And then I got 0 plus 1 is 1, so I got 12. So when x is 0, y is 12. 0, 12. Now, that's all we need in order to sketch this graph. Because listen to what we said earlier. When the multiplicity is even, it bounces. So that means that that curve, when it comes back here to just minus 1, it don't go through there. It has to bounce. Now, the multiplicity of my x minus 6 factor was 1. That's odd. So that says that it has to come down through here. So that's what the sketch of this curve is like. And it is very easy to do, thinking about this multiplicity of where it bounces and where it goes through. The next thing that we need to talk about is the end behavior of the curve. Well, look at this thing right here. As x keeps getting bigger and bigger and bigger, y is going to keep getting more and more negative. Over here, as x gets more and more negative, y keeps getting more and more positive. But the end behavior, we can do something to shortcut this. Look at my original function up there. If I just throw away the factors and I just put in the letters and keep the powers the way they are. So all of a sudden, I've got minus 2x cubed. So this graph that we're going to draw is going to behave just like this cubic function. Well, stop and think about it. If you let x get positive, you cube it, it still stays positive, and you multiply it times a negative, it's negative. So that's going to do exactly what we say here. As x gets more positive, my curve gets more negative. If you go the other way, if you let x be negative, a negative cubed is negative, but a negative 2 times negative is positive. So that simply means that it's doing exactly what we see here. As x gets bigger, y gets more negative. As x gets more negative, y gets more positive. So one of your homework problems is going to go like this. Now I want you to notice what we're saying this thing does. This thing bounced downward at the origin. It bounces again at 1, but it goes through 2. So he's going to give you a series of equations and say, which one of these could match this? Well, let's see. If I make it like this. The multiplicity at 0 is 2. Well, that means that it could bounce. And the multiplicity at 1 is 2. That means that it would bounce. The multiplicity at 2 is odd, so that means that it goes through it. So this simple little equation right here could match this particular graph. And look at all we did. The only thing we did was look at the multiplicity. It bounced at 0, it bounced at 1, and it went through at 2. So that means that this equation could be an equation for that. Let's see if we could possibly make up another one. If I made this x to the 4th and kept this an x minus 1 to the 2nd and an x minus 2 to the 3rd, I still had the same situation. This multiplicity is even, so it bounces. This multiplicity is even, so it bounced. This multiplicity is odd, so it went through the graph. Okay, let's go to section 5.2. 5.2 is a different ball game. Rational functions. Okay, we need to go back and remember what rational numbers are. 3/4 is a rational number. 5/16 is a rational number. 8 is a rational number. A rational number is any number that can be expressed as 2 integers. Now, I didn't just say fraction, because the square root of 5 divided by 3 is not a rational number. And it's not a rational number because the square root of 5 is not rational, because it can't be expressed as the quotient of 2 integers. Okay, so a rational function then, a rational function is going to be one function divided by another function. Now we get in trouble with this. There's some problems with our domain. Let's take a very good example. And it'd be a good one for us to start off with. Now, 1 divided by x squared minus 4. The first thing we got to realize that, hey, this thing right here has some x's I can't use. So we look at the x squared minus 4, and we solve that equation. So that means that x can't be 2 and x can't be minus 2. That would make this denominator 0, and we can't have that. Now, watch this message, what that does to help us to draw a graph. So when x is 2 and when x is minus 2. So I'm going to draw a dotted vertical line at x is equal to 2, and I'm going to draw a dotted vertical line at x is minus 2. That graph can't touch those two vertical lines. Now, I'm going to go ahead and do it, and we'll talk about it a little bit later. This thing also has a horizontal asymptote of the x-axis. And we'll talk about why that's true. But keep in mind, all I've done so far, we've decided that I can't use an x value of 2. I can't use an x value of minus 2. And I'm just telling you that as x gets really big, y is going to get close to 0. We could look at that simply from a number standpoint. Stop, think about it. If you let x be even 10, then you get 1 over 100 minus 4, you get 1 over 96. Well, 1 over 96 is very close to 0. But if you let x be 100, you've got a really, really small number. So y is equal to 0 is my horizontal asymptote. Now, so since I know where my asymptotes are, let's just get numbers in each one of these regions and see what the graph looks like. So let's move just to the right of this 2. Let's let x be 3. Well, if I let x be 3, I got 1 divided by 9 minus 4, which is 1 over 5. So when x is 3, then my y value is 1/5. Now, these are asymptotes, so this thing has to be hemmed in by these numbers. Now, we need to start using what we've learned a long time ago. This is not only helpful then, it's very helpful now. This is an even function. And since it's even, it is symmetric to the y-axis. So whatever I have over here, I'm going to have the same thing over here. But we can put in numbers and verify that. If you let x be minus 3, you still get 1 over 9 minus 4. And that's going to correspond to this 3 1/5 that we have here. Now, so the only thing we need to do is to go past that and see what happens between these two vertical lines. Take the easy point, let x be 0. When x is 0, I'm going to exaggerate it so we can see it right here. It's minus 1/4. Now, watch what happens with the idea of the asymptote again. Let's let x get really close to 2. Now, we know that x can't be 2. But if I let x be 1.9, then I have 1 divided by 1.9 squared minus 4. I don't know what the number is, but I know it's negative. So that means that it has to come up here like this. And since it's an even function, then that means that it has to come over this way also. Okay. Now we've taken the easier kind. In fact, there are 3 situations, and let's look at all 3 situations. Okay, when the power of the top is less than the power of the bottom, then every time y is equal to 0 is going to be your horizontal asymptote. So that's very, very important. Now, if you look back at what we just did, the power of the top up here was x is 0. The power of the top of the bottom is x is equal to 2. So the power of the top is less than the power of the bottom. And therefore, my horizontal asymptote was y is equal to 0. But that's what we work this thing off of when y is equal to 0. Now, you have the other situation. When the power of the top is equal to the power of the bottom. It's easier for me to put this down in symbols and let you see what it is right here. Now, this is simply an example. We're not going to draw this graph. But when the power of the top is equal to the power of the bottom, then the ratio of these coefficients is your horizontal asymptote. So my horizontal asymptote is going to be y is a divided by b. Okay, power of the top is equal to the power of the bottom. Your horizontal asymptote is going to be the ratio of these two numbers of a divided by b. So let's make an equation like that now. Okay. So we made us one up when the power of the top is equal to the power of the bottom. It's a bad example because my A and B is both the same thing, but that's beside the point. So in this particular problem, my horizontal asymptote is going to be 1 over 1, which is 1. So that is my horizontal asymptote. Now my two vertical asymptotes are going to be easy to find. So x squared minus 9 is 0, x is plus or minus 3. Okay. So I got a vertical asymptote at 3. I got a vertical asymptote at negative 3. I have a horizontal asymptote at y is equal to 1. Well, y is equal to 1 would be right in here. Okay, so I'm going to draw me a vertical line at 3. I'm going to draw me a vertical line at minus 3. Okay, now keep in mind, y is equal to 1 was my horizontal asymptote. I have a vertical asymptote at 3, I have a vertical asymptote at minus 3. Now remember, way back there, I made this comment. The graph will never cross the vertical asymptote. It can't cross is what makes the denominator 0. But it may cross the horizontal asymptote for regular values of the variable. And this is not one that does that, thank the Lord, but I'm going to show you what I'm talking about. Our horizontal asymptote was y is equal to 1. So 1 is equal to x squared plus x plus 1 divided by x squared plus 9. And you solve that. You get x squared plus 9 is x squared plus 1. And it won't work. That's good. That simply means that in this particular case, it didn't cross that horizontal asymptote. Now, drawing the graphs are going to be simple. You're going to let x be 4. You're going to go just to the right of this number. So you let x be equal to 4. And I got 16 plus 1, which is 17. And I got 16 minus 9, which is going to be 7. So when I let x be 4, I come out with 17 divided by 7. That's my point here. So my curve has to be hemmed in by this. It's an even function. So I'm going to have the same thing back over here on this side. So all I've got to do now is see what happens between. So when x is 0, I got 1 over minus 9. So we can put that here in minus 9. Now, so as it gets closer to 3 here, it's going to come. And as it gets closer to 3 here, it's going to come. So using the idea of the asymptotes and hemming the things in, it makes the sketching of our graph very simple. I might make this comment. When you start putting this into your calculator, you put the entire top in parentheses when you go to the y-z mode, and you took the entire bottom in parentheses in order for that curve to give you the correct graph. Now we got the third situation. When the power of the top is greater than the power of the bottom. Well, believe it or not, folks, we got to go back to the 4th grade to review something in order to be able to do this. And this is something that many of us haven't done in years and years and years. And this is the idea of long division. Let's take a perfect example. I'm going to divide 36 into 875. Well, it don't go, so it goes into 87. Oh, what, 2 times? And then you multiply. 2 6s is 12. Carry 1, 6, and 1 is 7. And then our next step was to subtract. So we subtract and we get 5. And then I bring down my 5. Now 36 will go into 55 one time. And this gives me a remainder of 11. Now, think back in your 4th grade. the way you check this answer, you multiplied your quotient you got times your divisor, and then you added your remainder. Listen to that again. We multiplied the quotient times the divisor, and then we added our remainder. Well, if you look at that from a algebra standpoint, this says that we got an answer of 21, and then I had a remainder of 11, and we always wrote our remainder over our divisor. So now, so this is our answer. This is my quotient plus my remainder. If I multiply that by 36, that'll do exactly what we just said. Multiply this, 36 cancels, so that means that we add our remainder. So what it says then, when the power of the top is greater than the power of the bottom with our polynomial functions, you're going to get what we call a slant asymptote, or they may call it oblique. I'd rather call it slant. Okay, so one of the first things we need to do is to get used to the idea of long division when we're using letters instead of just numbers. So let's take a simple one. Okay. X will go into x squared, x to the first time. So this is my quotient. I multiply x times x is x squared, x times minus 2 is minus 2x. My next step up here was to subtract that 72. So in algebra, we're going to subtract by changing the signs. So I'm subtracting this, so that means I had to change the sign. So this gives me a 5x and a 2x, which is a 7x, and then I bring down my number. Now, x will go into 7x 7 times. So 6 times 7x is 7x, and then I get minus 14, and then I subtract. And so this time I get a remainder of 28. But the beautiful part about it, we don't worry about this remainder. This right here is our slant asymptote. So our slant asymptote for this equation would be y is equal to x plus 7. And you say, well, why do you just throw away the remainder? Well, I want you to keep in mind what we said. The remainder over your divisor is the way that you really write it. Now, I want you to look at this. My remainder is going to be 28 divided by this x minus 2. For very large values of x, look what happens. If you let x be 100, this would be 28 divided by 98. If you let x be 1,000, this would be very, very small. In other words, what I'm saying is that your remainder simply goes away because you're only going to consider it for very large values of the variable. There were a couple of definitions that I didn't throw in right here. And one of those definitions is what we mean by proper function. Well, the proper is that first situation. The power of top is less than the power of the bottom. Okay, that's a proper fraction. And I think you have to use that. Going to cross the horizontal asymptote. I think I can make that just right here. Okay, so first of all, the power of the top is less than the power of the bottom. So what that says then is that my horizontal asymptote is going to be y is equal to 0. That's the easiest one for us to deal with, okay? Now, let's take care of that mess right now. Does it cross this horizontal asymptote? Well, take your equation. Multiply by this denominator, and you get 0 is equal to x minus 1. So 1 is equal to x. So it crosses at x is equal to 1. Okay. Now watch the graph. My two vertical asymptotes are 2 and minus 2, because they're the two things that make this denominator 0. We just said the horizontal asymptote is the x-axis, y is equal to 0. Now, we also just found out that when y is 0, x is 1. So that's right here. When x was 1, y was 0. Well, you say it's not a big deal. Yes, it's a big deal, because this is one where it does cross the horizontal asymptote, which is at 1, 0. Now, as far as drawing the rest of the graph, is no big deal. So this was x is equal to 2. So we're going to let x be 3. So when I let x be 3, I got 3 minus 1, which is 2, divided by 9 minus 4, which is 5. So when I let x be 3, my y comes out to be 2/5. So I know that that graph has to be hemmed in, because it can't cross this asymptote anywhere else except back here. Now, we didn't get quite as lucky this time. This is not an even function, because I had a power of x that's odd. So we have to get our other value. So this is minus 2. So let's come back here and let x be minus 3. Well, then this gives me minus 4 divided by 9 minus 4, which is 5. So it's minus 4/5. So in this particular case, then, when I let it be minus 3, I get minus 4/5. So the graph has to be in here. Now, this is odd. I want you to watch what's fixing to happen with this next mess. We already know that 1, 0 is where that thing crossed. Now, so let's let x be 0. If I let x be 0, then I got minus 1 divided by minus 4, which is 1/4. I'm going to put it up here to exaggerate it so we can see it. So when x is 0, y is 1/4. Now keep in mind, this is an asymptote. This over here is another asymptote. That thing don't have any choice, folks. It has to come down here, and it has to come back up here. Okay. Your calculator should simply be a good backup for you. You should be able to draw every one of these graphs using these concepts that we use. Good luck.